So the capacitor, it's a frequency controlled resistor. Let's take a look at it. First of all, we have here a voltage source, a resistor to represent the line resistance. It's 1 ohm. It basically doesn't exist in there, so we don't take account of that. And we have the capacitor. And right now we have 0 amps on the amp meter because this is a DC circuit. So why do we have 0 amps over here? We have the impedance of the capacitor XC, which equals 1 over 2 pi frequency times the capacitance, and we don't have any frequency, so the frequency is 0, so 1 over 0 equals a lot. A lot of impedance, or in layman's term, resistance, because they're both measured in ohms. And let's change that. Let's change it to AC voltage. Apply and OK. Now we can see there's some sort of amperage going through there. We can see it's going one way and another. That's why it's alternating. And let's see. This amp meter here is basically useless, so I'll remove that. And I'll add the oscilloscope image, which shows us a lot of information. Maybe a little bit too much information. Let's remove some of it. We don't need the voltage because it's the same on both sides of the circuit. It's just differed by the 1 ohm resistor. So let's see, remove the voltage, and let's see the negative peak value as well. It is a little bit off on the screen, but I can tell you that it's plus 12.57 on the upper peak and minus 12.7 on the lower peak. So, according to that formula, we can change the resistance or the impedance of the circuit with the value of the capacitor. Let's change it from 10 microfarads to 20 microfarads. And right away we can see that the amperage has gone up from 12 milliamps to 13 milliamps, and that means that the conductivity has increased and the resistance has gone down. We have changed the resistance of the circuit. Okay, that's alright, but still, capacitor is a frequency controlled resistor. They did not tell me that at school. At least they did not tell me that at school. Let's change the frequency. Let's change it from 40 Hertz to 400 Hertz. And the amperage has gone from 25 milliamps to 250 milliamps. That's actually quite linear in this case. So we can see that the higher the frequency, the higher amperage. That shows that the higher the conductivity of the circuit, and that means that the resistance is lower. A capacitor is a frequency controlled resistor which has lower resistance at higher frequency, unlike inductors which have lower resistance at lower frequencies. So let's take a look at this formula once again. 1, 2 and pi are constants. They don't really matter to us at this moment. And C, or the capacitance, usually is the same unless we use variable capacitors. So the only thing that can vary is the frequency, and very often it does vary. And we can simplify this equation to that one. I replace the impedance with resistance because they're both measured in ohms. I still have to keep the 1 over f, and I lose the 2 pi and c because they're constant values and don't really matter if we look at the change of the impedance or resistance. So we can see that the higher the frequency, the lower the resistance. And let's look at some other examples from faststop.com/circuits. Here we can see one. They're exactly the same circuits with the same capacitance, the same resistance, the same voltage sources. The only difference being that the voltage source frequency is different. It's 15, 40 and 80 Hertz. So the lower the frequency, the lower the amperage or higher resistance. The higher the frequency, the higher amperage and thus lower resistance. And once again, higher frequency, higher amperage, lower resistance, even more. And another schematic that I'd like to discuss is that one. A really simple schematic. Voltage source, capacitance, and line resistance. Basically line resistance, that's what the resistor does in here. And we can see that there is current. The yellow line is current, the green line is voltage. We can see that there is current, although this is a DC circuit which should have infinite impedance or resistance. But during a small time, which has been 223 milliseconds at this moment, during this time the capacitor was charging, and during charging or discharging we can see some current going through the capacitor. Let's look at it closer. Once again, charging, we can see current. Discharging, we can see the current is going to the opposite side on the graph, and also on the schematic itself we can see that the yellow dots are going one way and another way. And if we have alternating current going through the capacitor, it has a steady current going through it. Alternating, but still it has a steady current going through it. Now why is it doing that? I'll slow down the simulation, I'll reset it, and we can see that, let's just reset it like this. In the beginning, here's plus 5 volts, here's 0 volts, here's 0 volts, here's 0, everything else is 0 except for this line over here. If I connect it, the capacitor starts charging up. The positive charge is formulating on the upper plate and the negative charge on the lower plate. So we can see that it starts off with 0, 0, but eventually it'll be fully charged. When fully charged, the upper plate has the same potential than the upper side or the positive side of the voltage source, and the lower plate has the same potential as the negative side of the voltage source. So if the potentials are the same, eventually they will be, and the capacitor is fully charged, then there can't be any current going through, because for the current to move, it needs potential difference. It needs to go from higher potential through the schematic to the lower potential. But if the potentials are the same, there won't be any current going through here. So thanks for watching.